Okay, guys. So, welcome to uh, this week's topic. And this week we will talk about connected sets and its relationship to continuous functions. Uh, okay, I'm trying to adjust my thing so that thing would be more visible. And so far, I'm not succeeding. So, give me a minute. That's better, right? Okay. So, what I want to talk about is connected sets, and connected sets is the last section in chapter 2 that has to do with topology, and you will see why topology comes in. So let's talk about connected sets. And once again, just like with continuous functions, you have an intuitive notion of connected sets. So for instance, if I take this set over here, you will probably all agree with me that it's connected. And even though I'm going to commit a fundamental crime here, I will say that it's connected because if I take two different points in this set, I somehow can go with a line which completely belongs to the set and connect those 2 points. And this line is continuous. It's kind of a contradiction in terms because I already defined continuity. So now I'm talking about connected sets, and in chapter 2, we haven't defined continuity yet. So I'm just committing this intuitive abstraction. On the other hand, if I take this set, so this is one big set over here. And if I take this one big set, you will probably agree with me that it's disconnected because if I have this point and this point, there is no way for me to go from this point to this point in some sort of a continuous fashion. So what is a connected and disconnected set? And intuitively, if you look at this particular picture, you will say that a set is disconnected if a set E is a union of two sets, A union B, such that A and B are disjoint. Right? Like if you have a set A here and if you have a set B here, and if there is these two sets are disjoint, then the A union B is probably disconnected. However, this is not quite true. It all depends on how disjoint the sets are. So, for instance, if I take an interval, I don't know, 0, 2, so this is a subset of R. I hope you all will agree with me that this set is connected. However, what I can do is I can take a point 1 in here, and I will take a set A to be equal to 0, 1, including 1, and a set B to be equal to 1, 2, and 1 is excluded in a set B. And so as a result, A and B is an empty set. So these two sets are disjoint. However, A union B is equal to 0, 2, which intuitively should be a connected set. So what I have to do is I have to somehow set a notion of more than two sets being disjoint. So again, if I look at this picture, these two sets are not disjoint, but there is some distance between them. So they're really, really, really disjoint. And so what Rudin does here is he introduces a definition that I will introduce too in a second. Uh, I just want to change the page here. And the definition goes as follows. Let A and B be subsets of a metric space X So X here is a metric space. A and B are called separated, and this is a definition of separated sets. So A and B are called separated if they're a little bit more than disjoint. If A intersected B closure is empty, and B intersected A closure is also empty. So this is a little bit more than just being disjoint. And this is why it's called separated. So for instance, again, if you go to this interval 0, 2, like we did last time, and this is equal to the set 0, 1, union with 1, 2, then these two sets A and B over here are disjoint. The intersection of these two sets are empty. On the other hand, if I take A and intersect it with a closure of B, I will have a point 1 in there because the closure of B is a whole interval 1, 2, and I will have the situation that this particular set is not a union of two disjoint sets. Okay, so this is a definition of disjoint sets. These definitions you have to know. It may be on the test, on the last test of the semester. Uh, However, you have to have this understanding that disjoint doesn't mean that two sets are just that separated doesn't mean that two sets are just disjoint. It means that they're a little bit more than disjoint. Now, as always, there is an intuitive feeling of connected sets that we all have, and yet the topology comes in. This is not surprising. It happens very, very often in mathematics that even though intuitively something is clear, then either algebra or topology or something like that comes in if you want to make straight definitions. Okay, so now let's make a definition of a set E in a metric space X is not connected if E is a union of two sets A and B, where A and B are separated. So not just disjoint, but separated, which is a little bit stronger. This is a definition of what does it mean to be a set which is not connected. So for instance, in that example that I was giving you in a previous page, if I have set A and the set B, and this whole thing is a set E over here, then you can see that the set B is not just disjoint from the set A, but it's actually separated. So the closure of the set is this whole thing, and the intersection with A is empty. Likewise, the closure of A is this whole thing, and its intersection with B is empty. So this is the definition of not connected sets, and now we're going to give a very weird definition. A set is connected if it is, and I'm sorry for doing that, if it is not connected. Well, what does it mean? It means that the set cannot be written as a union of two separated sets. So this is a definition now. A set E in a metric space X is not connected, is connected, sorry, if it is not connected. In other words, if it cannot be written as a union of two separated sets. So this is a second definition that you will need. from this particular section. And it's kind of a little bit weird because, again, in the pictures I was drawing sets A and B, but the sets A and B are subsets of the same metric space X. And of course, whether the closures of sets depend not only on sets themselves, but on topology and on metric space X. But for now, this is a good definition. This definition is very, very, very similar to the definition that you may be learning in courses of topology. It is not quite the same as the definition of topology, and I don't want to go into topology too far, but this is kind of very similar to the topological definition of connected sets. And for those of you who are taking it, or those of you who will be taking topology, you will be dealing with connected sets a lot, and it's a very, 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 very important notion in topology. Okay, but for now, what I want to do is I want to prove just one theorem, and this is the theorem about connected sets. In a particular metric space R. And of course, if I talk about particular metric space R, I mean that the distance between 2 points x and y is equal to x minus y, so it's usual distance. And I want to characterize the connected sets in a set R. And here is the theorem. It is the theorem 247 in Rudin. And the theorem says that, so this is a theorem that I will deal with proving in a minute. The theorem says that a set E in R is connected if and only if, so notice that if and only if, uh, for every x and y in E, so these are two numbers, x and y, and they're not equal, so I will assume that x is less than y. And if z is between x and y, then z belongs to E. So this is the theorem. It says that the set is connected if and only if it has this kind of intermediate value property, if and only if you take a point x, so this is your space R, you take a point x and a point y in E, and you take any point z in between, and this point z in between has to belong to E. In that case, the set in R is connected. So in particular, for instance, this interval over here, 0, 1, is a connected set because no matter where you take 2 points in this set and another point in between, if the two sets belong to the set E, then the point is between belongs there. This set 0, 1 is likewise a connected set, and this set 0, 1 is also a connected set. Okay, so what this theorem says is that this particular in-betweenness property completely characterizes the connected sets in the metric space of all real numbers. Again, I'm trying to position my paper so that it will be the most visible. So you understand the meaning of the theorem. There are two theorems here. It says that, first of all, if the set is connected, x and y is in E, and z is between x and y, and z belongs to E. The second statement says that if the set E has this properties that for every x and y in E and every z between x and y, z belongs to E, then the set is connected in a sense that it cannot be written as a union of two disjoint sets. Okay, so I'm not giving you a proof yet. I will just want to work on a proof. And in a picture, you will say, well, let's take real line. And let's take a set A in here, and let's take a set B in here. And if you take a point x in here and a point y in here, then there is a point z in between that does not belong to the union of A and B, and so it is not connected. And this is basically how the proof will go, except my sets, remember, in a real line, can look very, very weird. So the set A may consist of a whole bunch of points like this, and a set B, I'm going to try to use a different color if it will be visible, and the set B will look somewhere in between. So the points in a set B and the points in a set A may be meshed together, and this is why we need a little bit of a proof here. So in order to make this proof more exact, what we want to do is we want to make a notation. So in this case, let's suppose that X and Y is in E. And again, I'm assuming without loss of generality that X is less than Z, which is less than Y. And what I want to do is I want to say that if E is connected, meaning if E cannot be written as a union of two separated sets, then Z belongs to E. And remember this picture that I was showing you that the two sets can be very mixed up. So what I introduced together with Rudin is the set A sub Z, and this is the set of those points in E which are between minus infinity and Z. Notice that this is an open interval between minus infinity and Z, and the set B of Z will be, of course, the set E intersected with Z infinity. So whatever my set E is, it could be very weird. What I'm going to do is I'm going to take a point Z in this set, or not in this set, and I'm going to take these two sets up to Z, being the set A sub Z and B sub Z, and this is the definitions of my sets A sub Z and Z sub Z. Okay, so X being less than Z, X belongs to E, right? And X is less than Z, so it belongs to this set, and therefore X is an A sub Z. Likewise, Y, well, Y is greater than Z, and so it belongs to the set Z infinity, and it also belongs to the set E, so Y is a set B sub Z. Do you agree with me? Yes. So now let's suppose that Z does not belong to E, right? So this is kind of a proof by contradiction. Then what happens if I take A sub Z intersected with B sub Z? Well, it will contain everything in E, but it will be between minus infinity and Z, including Z. So A sub Z will be somewhere in whatever E intersected with minus infinity Z. And if Z does not belong there, then that means that this set intersected with this set B sub Z over here will be empty. Likewise, if Z does not belong here, what will be the closure of B sub Z? Well, the closure of B sub Z will be everything here, including Z itself. And that will mean that A sub Z intersected with B sub Z is empty. And so since the set E is equal to those elements of E which between minus infinity and Z, union with those elements which are between Z and infinity. Remember, Z does not belong to the set E. That means that E is not connected. And we have a contradiction. So what we proved here so far, we proved that if the set has a property is that for every x and y, uh, there exists a z between x and y, or for some x and y, there exists a z between x and y, such that z does not belong to the set, then the set is not connected. In other words, what we proved here, that if the set is connected, then this particular property is true. Now we want to prove the converse, and the converse is a little bit more complicated. So I apologize for a complicated proof, but this is the best I can do at the moment, given the circumstances and everything else. So now I'm going to assume that the set E is not connected. And I want to prove that there exists x less than y, x and y in E, and there exists a z between x and y, so z is between x and y, such that z is not an E. So this is a converse to that theorem. A converse to that theorem will say that if the set is not connected, in other words, if it can be written as a union of two separated sets, then there are always x and y with this property and a z with this property, such that z does not belong there. Okay, so the proof goes as follows, and the proof will go in two steps, and the second step will be a little bit weird. So what I'm going to do is I'm going to take a set x, which is less than y, a point x, which is less than y, and the points x and y are going to be in E, and I'm going to look, I'm going to assume that E can be written as a union of two separated sets, A and B. Okay, and what I'm going to do is I'm going to pick a point z. So the point z will be somewhere between x and y, and I'm going to pick it very, very carefully. I'm going to pick the point z as being supremum of a intersected with an interval x, y. In other words, what I'm doing is I'm taking this first set a over here. Uh, so x is in a, and y is in b, right? So E is equal to A union B. I'm picking X and A, Y and B, and I'm picking the point B, which is in this supremum. Uh, I don't know how to draw a picture of it. Again, there is A union B, so the point X is an A. Somewhere here there is an A, and somewhere here there is the point Y, which is in B. These two sets are separated, and what I'm going to do is I'm going to look at the supremum of all points in here. So the supremum here of A intersected with xy will be somewhere here. And there are two possibilities. Z, of course, well, Z is in the supremum of the set, so Z is definitely in the closure of the set A, right? Because supremum always belongs to the closure of the set. So in particular, Z is in the closure of the set A, and therefore Z is not in B, right? Because the closure of A and the closure of B have empty, the closure of A and B have empty intersection. And so what we conclude is that Z is less than Y and greater or equal than X. Okay. And now I know that there are two possibilities. One, Z is not an A. If Z is not an A, then I'm done. I can find a point Z, which is between X and Y. It is not an A, it is not in B, and therefore it is not in A union B. So if Z is in not an A, then I'm done with my problem. The second possibility is that Z is an A. Okay, so not only it's in a closure of A, but it's actually in A. That implies that Z is not in the closure of B. Well, why not? Because remember, A and B are separated, so intersection of A and B star is empty, and therefore Z cannot be in the closure of B. And that means that there exists a Z1, which is somewhere between Y and that Z over here, that very Z that we uh, so carefully selected, such that Z1 is not in B. Remember, Z is not in B bar. That means that there exists some point not in B, which is very close than Z, and this is my point Z1. And this point Z1 is somewhere between Z and Y. And what did we conclude? Z1 is not in B, Z1 is not in A. Now, we assume that Z was in A and Y was in B. And so that implies that there exists a point Z1 between y and z in this case. So z is a point in A, y is a point in B, and this point z1 is not in the union of A, B. So the second situation needs a little bit of talking through, and I hope you will listen to my lectures, and I hope you will also read the book several times, because this is kind of a weird part of a proof. It's not too difficult, it's not too hard, but this is a part of a proof. So again, what we proved here is the following statement that, and this will be important for us later on, that a set E in R is connected. In other words, it cannot be written as a union of two separated sets if and only if for every x and y in E with the properties that x is less than y, and for every point z between y and x, z belongs to E. Okay, so again, if you look at this picture over here, and if this is your set E, then, well, the picture has to be in a real line. So let me do a different picture. If you look at this picture over here, and you look at another picture over here, if x is in here and y is in here, there is a point z which is in between, and therefore the set is not connected. On the other hand, if you look at the intervals that we were talking about from the very beginning, interval 0, 2, you pick any point, any 2 points in this interval, x and y, and you pick any point z in between those two intervals. This point z will belong to this interval, and because it has this property, we can conclude using the theorems that we just proved that the set is connected. So this kind of intermediate point property is the characterization of connected sets in R. Okay, so now it comes close to half an hour, and I will continue with the next video.